that if this is movement onset and this is the readiness potential, then we say maybe that the information exists in the brain in the beginning of the readiness potential, but people report having decided using that rotating clock that I discussed before, only around here. So about 200 milliseconds before movement onset, they say they've decided, but about a second before movement onset, they say that, I mean, we see this readiness potential in the brain. Again, this is well-known results. And so the intuitive order of events is this. However, in the Libet experiment, we see that there's information that exists in the brain before the onset of the conscious decision, which tends to puzzle people, right? Like what's going on in this time interval. So perhaps if the information already exists in the brain, but you have not reported being consciously aware of it, then perhaps this decision was already made unconsciously. So a Libet type of decision that I described here, raise one of your hands for no reason and no purpose, is a type of arbitrary decision. There are other arbitrary decisions that we make in life. Imagine driving down a three-lane highway and you see that the lane in front of you is closed. Well, you can overtake this barrier from the left, you can overtake it from the right. It doesn't really matter what you do, assuming this is the highway is empty. So it's an arbitrary decision. You just have to, in some sense, break the symmetry of left versus right. Now imagine another situation. You're driving down the highway. Again, the lane is closed, but this time there's a car on your right. So in this situation, you would, I hope, not choose to go to the right, but rather overtake this obstacle from the left. So this time it's a deliberate decision. You have a reason to act. You act according to that reason. So, well, why do we care about deliberate decisions? I think there are a few reasons for that. I would argue perhaps that most decisions in life are deliberate, that there's some reason for your actions. You don't just lash out arbitrarily. It's also, I think, it is plausible that consciousness might be more involved in deliberate decisions than in arbitrary ones. So if you care about the involvement of consciousness in your actions, so that might be relevant. I guess that various decisions, especially decisions related to free will, and certainly those that relate more to the idea of moral responsibility, would be deliberate. I mean, it's hard to imagine somebody being morally responsible for raising their right hand and not their left hand for no reason and no purpose. As I mentioned before, arbitrary decisions, those that are unreasoned, especially if they're in the Libet style of purposeless and so on, they're some type of like a degenerate type of decision, right? You just have to break the symmetry. You have to raise one of your hands. Okay, whatever, I'll raise this one. So there are reasons why we might care about deliberate decisions, and we've done some work. This is work with Gideon Yaffe, Christoph Koch, and Liad Mudrik, where we showed actually that this readiness potential that exists in arbitrary decisions actually kind of goes away in deliberate decisions. What do you want me to do with questions? Answer as I see somebody raising their hand, or should I wait for questions later? What's the policy? Is it up to me? Well, I'm not hearing anything, so I'll take it up to me. So maybe I'll try to go through this and take questions at the end, just because I'm starting late. I'll try to plow
as you
through
prefer.
Okay, if that's okay. So let me just go through this, and please keep questions then for the end. If it's absolutely vital, let me know, but we are short on time anyway. Yeah, okay. So we have shown that, again, arbitrary decisions create this readiness potential, but at least in the task that we have chosen, and I spoke much more about that in June, this donation to NPOs. We see if we make the donation arbitrary, you get a nice readiness potential. If you make the donation deliberate, then in the usual sense of a donation, then we do not see the same readiness potential. So again, this is to say that I am personally invested in studying deliberate decisions. And I mean, we've done other work, and I actually, I think that some of my colleagues of late have started looking perhaps more into deliberate decisions than they did before. However, the vast majority of the literature in the neuroscience of volition has focused since really the seminal papers of Libet on arbitrary decisions. And on these types of things, right? So as such, I think that and I mean, it's just a few examples here, but intracranial recordings, fMRI, left versus right hand recordings, so work by Patrick Haggard, John Dylan Haynes, Itzhak Fried, Gabriel Kreiman, and other people, has really focused on arbitrary decisions. Yeah. So one thing to think about, so if we are now focusing more on arbitrary decisions, and especially if we want to, and again, I don't think we necessarily want to, but it seems that some in the field would like to equate freedom with arbitrariness. So I think it's interesting to test the limits of arbitrariness. So how arbitrary or random can humans be? And this is what I would like to talk to you more today. So there are some things we know about human randomness that have been known since the 60s and 70s. We know that human random sequence generation is limited. We can only be so random if we're just asked to create a series of zeros and ones. Then we are quite good at making it about half zeros and half ones. What we are not good about is representing long sequences of the same element. So if you create, let's say, a sequence of 100 or 200 zeros and ones, at some point it is actually quite likely that you would get 0, 0, 0, 0, 0, or 5 zeros in a row, 6 zeros in a row. Of course, you can compute the probability for that. But humans tend to underrepresent these long sequences of the same element, or as they're called, a run. So they underrepresent long runs. So they tend to switch too much. And when you switch too much, I mean, you become less random, less arbitrary. So again, this has been known for a while. There's also some evidence that human random sequence generation improves during a game. So if I ask you to play rock, paper, scissors, and you know that you have to be random to win, it seems that you would do better. What is unclear is whether that's because it's a competitive setting or because you get feedback in the game, but we know that in a game situation, you get better. You can become more random, but it was not clear how random you can become. So we set out to do this research with 4 research questions that we were interested in. One was the question of, well, we know people can become better during a game, but would it be different if we told them that they have to be random, right? If we instructed them to be as random as possible, or if we did not instruct them and they would just have to kind of figure it out from the game, would they get any better by being instructed? The second question we were interested in is, well, okay, people can become more random, but how random can they become? One of the reasons this was hard for us to find out, we realized that there were kind of, at least in the neuroscience/psychology studies of randomness, there weren't very good measures of randomness. And I'll talk more about that in a moment. People were looking at things like the length of runs and things like that, but yeah. Anyway, third research question was, okay, let's say you improve during a game situation. What happens after that? Does something stay? Does something stick? Does that transfer to just, if you're after the game told you just, okay, now generate a series of rock, paper, scissors, just rock, rock, paper, scissors, rock, and so on. Would you still stay more random? And then, again, we saw from the literature that there's this idea that perhaps the random sequence generation is related to run length. So, so we wanted to try and understand that relation a bit more. So we came up with this paradigm. We asked people to basically the game was rock, paper, scissors. But before the game, we just asked you to create a sequence of 200 rock, paper, or scissors and be as random as possible. So again, it would be something like, rock, paper, scissors, scissors, rock, paper, scissors. Then you played a game of rock, paper, scissors. And then after the game, we asked you to create another series of rock, paper, scissors. During the game, there were 3 different conditions that were between subjects. So each subject was in only one of these conditions. Some people, we told them that they're going to play rock, paper, scissors against the computer. And they were not told, I'm sorry, I think there's a mistake here on the slide. They were not told anything about what the computer would do. They were just told to win. In the aware condition, they were specifically told that the computer will exploit any kind of pattern that it finds in their behavior against them. Oh, see, there are 2 errors. I'm sorry. This is unaware. Condition 2 is aware. I made a lot of, I apologize. So condition 1 is unaware. Condition 2 is aware. Condition 3 is control. Again, in the unaware, you're just told to play against the computer and win. In the aware condition, you're told the computer would exploit any kind of pattern in your behavior against you. So you had better be as random as you can. That's the condition 2. Condition 3 is a control condition. Basically, the point was to try to create a situation where the computer just does not do anything specifically random. So the computer just went rock, paper, scissors with 85% probability. And then with 15% probability, the computer just did something random. So 85% of the time, you just create this series of rock, paper, scissors. So that's the experimental task. And then in every trial, what you see happening is there's a 3, 2, 1, go. And at the go signal, if it's one of the random sequence generation ones, you just, you have to press, I believe it was, keys on the keyboard for rock, paper, or scissors. And you have to press that within 500 milliseconds of the go signal. That's in the experimental task and the random sequence generation before or after the game. During the game, you do the same thing, but now you get feedback about what the computer did, and your points rise or fall depending if you win or lose or tie in rock, paper, scissors. So tie, nobody gets points, or both get points. I actually don't remember. And if you win, you get a point, and the computer doesn't. If you lose, the computer gets a point and you don't. Right, so this is the task. I mentioned that we could not find very good measures of randomness, so we developed our own. Well, this measure has been used before, but not so much in psychology and neuroscience. The idea is to think about randomness as lack of patterns. If you have a series that is not random, something like this, if you have 10 zeros and 10 ones, then it's easy to describe it as 10 times 0 and then 10 times 1. But if you have a series that is random, then it's much harder to compress it into something like this. So we just used, we looked at Lempel-Zeev complexity, which is a lossless compression algorithm that a lot of us use on our computers to compress things. But again, it's lossless, so you can decompress it and get exactly the same thing back. So we developed something based on that. I'm not going to go too much details given the time, but we basically the thing was how compressible is it, and you got a score closer to 0 meant that it's less.
Uri, are you there?
Somebody called my name.
Okay, so you froze.
Oh, can you guys hear me now?
Yes.
I'm sorry. Should I repeat anything or?
Yeah, please go back as one slide. Yeah.
Okay. So the LZC score is a measure of randomness based on patterns. So how the more patterns that are found, the less random that you are. So if this measure is around 0 or smaller, then you're less random. If it's higher, then you're more random. And so this kind of lives between 0 and 1, with 1, although it can go a little bit above 1 as well. Yeah. So the subjects did this whole experiment, and then after the experiment, they were given a questionnaire with these 7 questions here, asking about whether they used a strategy, whether they felt the computer was predicting them, were they able to create random sequences before and after the game, did they feel that their post-game sequence was more random than the pre-game sequence, and then we asked them, like, who won more trials during the game. Did you win more trials during the game? Did you tie most of the trials during the game, or did you lose most of the trials during the game? These are the questions we asked everyone. Okay. I should say we created this algorithm that really does try to find any pattern that it can in your rock paper scissors sequence. Also, it tried to look to find patterns about winning and losing. So let's say if every time you won, you would switch, or sorry, I mean, some people do what's called the win, stay, lose, switch. So if you win, you maybe try the same thing again. If you lose, you try something else. So it would pick up basically on anything that at least that we could conceive that you could do. And you can see it worked quite well. So in the unaware and aware conditions, these are the subjects. It's sorted by the difference. So anything below 0 means the subject's lost. And you can see that very few subjects were able to beat the computer. And in contrast, in the control condition, where the computer was being very unrandom and we would expect people to beat the computer, you can see that most subjects beat the computer. So it seems that this manipulation at least worked. So what did we get? This is this normalized LZC score. Again, scores around closer to 1 mean that you were more random. So in the unaware, I mean, I'm leaving out the control condition for most of this because it's, I mean, we tested it, it did work, and it's perhaps less interesting. I will show one slide about it later, but I will focus on the unaware versus aware conditions. So what I think you can see here is that in both the unaware and the aware condition, in these violin plots, people tended to be less random during the pregame, then they were more random during the game, and then again less random in the postgame. You can see that it's roughly the same in both of them. Another thing to see here is this bootstrap distribution that is here. This is an attempt to try to understand how random people are. So what we did was we created the same sequence, a sequence of the same length as these people, but this time we just used Python's random number generator. It uses the twister algorithm, and we created, I think, 10,000 sequences of length 200, and we just tried to see if we computed the same normalized LZC score on them, this is the distribution that we got. So from the 0.25%, so the 2.5 percentile to the 97.5th percentile, this is what you would kind of expect, right, to get by chance. This is higher than the computer, this is lower than the computer. Now, I think what is interesting here to see is that during the game, people got on some their average randomness was not statistically significantly different from Python's random number generator, but this only happened during the game, and then after the game, they decreased back. So, I mean, these are the actual numbers. So, because we also you can also look at the subject by subject. So 35 out of 51 were more random during the game than during the pre and post game, and 25 out of 48 in the aware. So in both situations, it's more than you would expect by chance for the binomial test. Right. Let's. This is. I told you that I also show you the control condition. So it's here. I mean, it's as you expect. So people now become less random during the game because they follow the pattern of the computer to beat it, and then become more random after the game. So let's go back to our research questions. The first one was, well, can human random sequence generation in the games improve further if we tell them to be random, right? If we tell them that they have to be random to win. So this is a comparison between this condition, I mean, the unaware and the aware, specifically in the game. I mean, if you do a statistical test between these two, you do not find any statistical significant differences between them. And I mean, the effect size is also quite small. I mean, you can see that there is a little bit of a difference, but the effect size is quite small. And if you do a Bayesian analysis, it actually suggests that there's evidence that there is no difference between them. So the BF10 is less than a third here. So it does not seem that humans can improve following instructions to be more random. The second question, well, how random can human random sequence generation get? So this, I mentioned that already. But basically, using this permutation test that I mentioned before, during the game, people get to that region where they are not significantly different from Python's random number generator, but then they decrease back afterwards. So this gets at the third question of, well, does this improved random sequence generation during the game, does that stay high or does it get lower? We have evidence to suggest that you can see it here, but you can also do the statistics and you can see that it does get lower before and after, but then comparing the before to the after, there's no significant differences. It rises, it goes back to where it was. That's what we see. So it does not seem that the improved random sequence generation during the game it does not remain high after the game. For the last question, we asked whether there are changes in the random sequence generation related to the run length. Again, a run is a sequence of the same elements. So rock, 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 that's a run. And then if you switch to whatever paper, then that becomes a new run. So if we look at run length, there's actually an interesting pattern. So this is the run length scores. This is a new graph. These are the scores I showed you before. So before, remember the LZ score, so the overall randomness, you became more random during the game, and then after the game you became less random. With the run length, however, your run length becomes longer. Again, remember, people underrepresent long runs. So the fact, if you become more random, we expect your runs to get longer, and we see this. But then after the game, interestingly here, you still stay statistically insignificantly different. So you don't seem to go back down to where you were. So people become more their run length become longer and they stay long, both in the unaware and the aware conditions. And that we thought is interesting. Now, if you look at the run length and you try to understand, I mean, this is trying to understand, okay, this randomness, okay, what really explains it? Or, I mean, we know that, let me put it differently. We know that run length explains, or that people underrepresent long runs, but we wanted to understand how much of the variance in the randomness is explained by that. So if we take like an overall, we look at all the conditions together, then we see that the average run length explains almost 20% of the variance in the normalized LZC score. If we do it condition by condition, we actually see that in the baseline, baseline in the game, it's closer to 30%, but in the post game, it's actually only around 11%. So it seems that the run length explains some, but certainly not all of the variance. Right. So this, it's interesting to think about this third one, right? The post game, to see that the R square there is especially low, but it's maybe not surprising given that we see this strange behavior in the post game where the run lengths stay long or stay longer, but the randomness decreases back to the situation where it was before. So it seems that people do learn from the game to increase the length of their runs, but their randomness stays low. So you would expect the run length to explain less of the variance. Now, I'll try to conclude again. I'm trying to do all this quickly. I'm sorry, given the time constraints. So first of all, just instructing people to be more random. Okay, if you're in this game environment, we know you become more random. Can you become even more random if we instruct you to be random? It doesn't seem to be the case. Also, when we asked subjects about it, they did not report that they used some kind of strategy in the aware that was different or more strategy or anything like that compared to the unaware condition. So subjects neither reported it, nor did we see any of that. We did see, as I mentioned before, that human random sequence generation has actually become quite random, or at least statistically indistinguishable from the pseudo-random generation of Python or other. I mean, Python uses the same algorithm as MATLAB and R and others, so you would not expect a difference. So it doesn't seem that subjects are able to further sorry, I think this is a mistake again. I'm sorry about this. But basically, it seems that subjects can become quite random during the game condition. Now, interestingly though, this randomness does not seem to be maintained after the game condition, although the run length does seem to stay longer. And when we ask people in the survey what they perceived, they didn't perceive that they were more or less random after the game, before the game, or anything like that. So it seems that that we were not able to see a transfer either implicitly as the way they played, or explicitly the way people said. So there just does not seem to be any transfer there. Last thing, as I mentioned, that the underrepresentation of these long runs explains something between 10 to about 30% of the variance. Now, why that is and what's going on there. So, I mean, one option, the run length specifically looks at runs of the same entry or item in the series, right? It's rock, 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 rock. But if you do something like rock, paper, scissors, rock, paper, scissors, rock, paper, scissors, the runs would be short because each run would be one. You switch all the time. However, you're not random. So we have to remember that run length, that for some reason for a long time was viewed as a measure of randomness in this field, is just honestly not a very good measure of randomness. It only tracks what are called unigrams. If you want to track something like rock, paper, scissors, this 3 gram or general n-gram, then it's just run length just doesn't track that. So it's not the right it's not the right thing. It's not the right measure. Yeah, so just to say a few other things. One question I think that still remains is what leads to the higher randomness in the game condition, because there are at least 2 aspects of this game that that could lead to that. One is the idea that it's a competitive situation, that you get these scores, you see if you win or you sorry, you get, well, one is the situation that you get the score, that you're in competition with someone. The other one is feedback, is that you get information after every trial, whether you won or you lost. So one thing we would like to do in the future is potentially tease those 2 apart, try competition without feedback, feedback without competition, and see what happens. The other thing that's of course interesting is, what explains the remaining 71 to 90% of the variance in the randomness beyond run length. Again, one thing could be that it's just not unigrams, it's something longer. It could also be, as you saw there, that the relation is just not linear. It seems like a kind of plateau, so there might just not be a linear relation. Other options that, people have been talking about, like maybe you utilize some kind of momentary neural noise in the brain to create randomness. So maybe that's something that's there. There's something to be perhaps said for that. You could think about situations in real life where it's useful to be random, from anything from a gazelle running away from a lion or something. It tends to make these kind of like zigzagging movements, and if you are predictable, then you become lunch, right? So becoming unpredictable, and one way to become unpredictable is to become random, is maybe useful. So you could think about utilizing some kind of neural noise for that. So maybe there's just, if we really do that, then maybe there is nothing that would explain everything in the randomness. There is work by Jahan Shahi suggesting what's called a network modulation model that suggests that maybe that you need some kind of like inhibition of stereotypical responses. That's perhaps, those are in the superior temporal cortex, and maybe that's done by the DLPFC. And there's some evidence that with TMS to the DLPFC, people become less random if it doesn't inhibit the stereotypical responses. But so maybe something there could explain some of this, but in our situation, we would then expect that perhaps the DLPFC to become more active during the game. We did not record EEG. That might be something for further studies, and that's something we could potentially look into. And I think, given the time, that I should stop here for some questions. Thank you again.
Okay, thank you, Uri. So, okay, Marcel is gonna start.
Hi, Uri.
Hey, Marcel.
Pity that you can't be here and stand with us in the line of the bank.
I know. I just for that I should have come. I know, but maybe you could come to LA and we could stand in a line in a bank here.
I don't know whether it's the same thing. Okay, so I have a point that you already raised yourself in the end of your talk. I was wondering whether people really learn randomness or whether they learn to respond to the feedback, and that happens to be random in a way, which is of course a different thing. And that might also explain why they can't maintain, or why they don't maintain this kind of randomness when the feedback falls away, because in principle, they are absolutely not random in a way because they respond to feedback. Do you see what I mean?
Yeah, and I see your point, and I think that's another reason to try to do this follow-up study, to really try to tease apart whether it's the feedback or if it's the whether it's the feedback or it's the competitiveness that gets people random. And I don't have an answer for you, but I agree with you that it could be one or the other. I mean, people are not that horribly unrandom, right? If you look at the slide that I had here, so I'm going to have to run like this for a moment, but I mean, let's take this slide. So, I mean, people do become more random, but it's not that they go from, zero would be complete non-randomness or something like that. So, but people are not horribly unrandom, but it is true that in this situation, there could be two things, as you say, and I wonder whether that's just really the feedback or not. So, and the way to do that is, you could have people play a game, but you give them feedback very rarely or something like that, right? And then you could see whether that influences their randomness. Or you could do the other way, where you give them feedback, but it's maybe not a game or something like that. They don't. But there's this feedback doesn't mean anything. So yeah, that's the way to tease this apart. The only sad situation is the student. For me, the student who worked on this is now finishing her PhD. So I'll have to find somebody else interested enough in randomness to look into this. But so I think it's an interesting and important question.
Okay, thanks.
Gabriel has a question too, but I have precedence. I have the mic. So Uri, thank you very much for your talk. I couldn't stop myself from remembering one of the talks in Chapman. You can help me. I don't remember exactly who it was, but the speaker was defending an evolutionary role for arbitrariness.
Is it Bjorn Brems?
Yeah, and he showed this video of a fish being eaten by a snake. Remember that?
Oh, was it you? I think maybe it was Bjorn Brems. I mean, I think I remember which. It was either that
he was German.
Yeah, Bjorn Brems, I think it was. Yeah.
Yes. Yeah. So that was very, very impacting video. The snake would tease the fish, and the fish would predictably run to the other side and would be eaten. And so his conclusion was that there is an evolutionary reason for being arbitrary, and as much as you said in the case of the gazelle. But my question is, would that hold for human beings? Because I mean, we are a very social group and very dependent on the behaviors of others. We have Tom and theory of mind and all these things. And being from law, it has been argued by this very influential philosopher, sociologist, Nicholas Luhmann, German as well, that law is about expecting, it's like about being able to predict or being predictable, to normalize expectations. I mean, you can go through a red light, a green light, because you expect that someone will see a red light in the other side, and then you can just go home. So does that arbitrariness hold for a social species like ours? And would this evolutionary role for arbitrariness be something for useful for human beings as well? I mean, as much as it could be for the fish not to be eaten by, or for the gazelle.
Right. Well, I guess if the snake was trying to eat you, it would be useful also to be random. But I mean, more specifically in the social settings, again, I mean, these are speculations. I don't have studies to back this up, or I don't know of the studies to back this up. But I think that humans, I mean, when your friends tell you, "Oh my God, you're so predictable," they're not giving you a compliment, right? They kind of mean that that you always do the same thing, and that every time they tease you this way, you're going to act like that. So I think that predicting others is useful. This depends on your view on human social interactions, whether you look at it as more of a competitive situation or more of a collaborative. It's probably somewhere in the middle, depending on the situation. But if you're trying to outmaneuver someone with whom you're competing for the same, I don't know, job or something like that, so knowing that they're going to do this and being able to, oh, they're going to go, I don't know, play golf with the boss over the weekend. So I will make sure before the weekend to already get on the boss's good side for this coming promotion, something along those lines. For you to be able to predict others, that's useful, but that of course means that for others to be or unpredictable is also useful. So I think that there is this ongoing, that there is an ongoing arms race in some sense of being unpredictable. I think is useful, but then predicting others better is also useful. So I mean, a theory like that would suggest that if we come back in 1,000 years and we are still here, maybe still in your guys' case, still standing in line in the bank. So, but if we're still here, then we might be able to be more random because this evolutionary arms race would continue. But besides these more speculative answers, I must honestly confess that I don't know. These are speculations.
Makes a lot of sense. Thank you.
Hi, Uri. Very nice talk. Thanks a lot. My question is about what kind of random algorithms do you use? Because it makes a difference. I mean, the great advances we had in algorithms to randomize number generation from gambling. So we have the Monte Carlo algorithm. We have the quicksort that's used, for example, in Las Vegas. But we have older stuff like Mersenn's algorithm. Even if you use MATLAB or you use Excel to generate a random number, a series of random numbers, they will behave really differently. And of course, they are pseudo-random. I mean, if there's a computer generating the numbers under some sort of logic, they are not really random. They are pseudo-random, right? And we have levels of randomness within those boundaries, right? So I don't know if I heard well, but did you say that makes no difference to use different random algorithms when you have confrontation between humans and the computer? Or do you think this is something that have to I mean, the follow-ups of your experiment have to be treated? Or I just want to hear a little bit more about the structure of the algorithms you used.
So we used Python's random number generator algorithm. In this case, it's the, if I remember correctly, it's the twister algorithm. So it's an improvement upon some of the earlier ones that you mentioned. Now, it is not cryptographic. It's not like a cryptographically random algorithm. Right. So it passes most of the random checks of the it's like I don't know what it's called. The association.
Did they go through Markov inequality, for example?
I think yes, but again, they failed. So there are whatever, like 15 tests that they exist. Okay. I think they failed 2 of the 15. They passed the others. However, I should say so. Two. I would answer the rest of this in 2 ways. One, if you ask philosophers, for instance, what exactly is randomness, you would probably get, or not probably, I've tried, you get different answers from different people about what randomness is and does it even exist in nature, and I mean, maybe in the quantum realm and so on. I did at some point, you could buy, I don't know, I mean, the fact that you could buy something doesn't mean that it's really, I mean, you can buy random series on the internet. You could go and buy a terabyte of random numbers on the internet. The fact that you can buy just means that there's somebody that thinks that they can make money off it. It doesn't mean that it's really random. But I think at some point, I'd have to ask Alice, who's the PhD student who did this, but at some point we got interested in this question and said, you know, is it just because of this? So if I remember correctly, at some point we didn't buy a terabyte, but we bought a little bit. And I think if memory serves, because we've been doing this project for a few years, if memory serves, we even tried to run it through these 15 tests, and I think we made sure that it is okay. And the results seem roughly the same here for if you run this shuffling approach that we did here. So, but again, this is all if memory serves. But the other thing that I was saying is that this twister algorithm that Python uses is the same one that now MATLAB uses, and I don't actually know what Excel uses. I don't honestly use much Excel, but I think, so basically I'm saying this is the common one, but you are absolutely correct. This is a pseudo random number generator. It's built on some kind of, you know, so chaos kind of like behavior and so on.
Yes. Right. And how do you, like, I think Marcel's question was great. It is a serious case of learning that could be going on in your experiments. If you had like devise any strategy to avoid learning, playing against the machine in those cases, if you have like future plans to try to avoid some sort of learning in those cases.
So I think that for the learning, you need feedback. And that's where I hope that if we run this again, this time, not providing feedback. So you play a game, but let's say only, I mean, the thought that we had was something like, let's say that only after every 20 trials, you get feedback about how many points you have and how many points the computer has. So you cannot on every trial improve, you just get feedback. So, I mean, it's an empirical question then, would the randomness drop or not? I mean, I think I would hypothesize with Marcel that the randomness then would decrease, that you would not be as random, but it remains to be tested. It's not a very hard experiment to do, but it remains to be tested. I don't know that anybody's done that. I haven't found any literature on that.
Hello, Uri. Santiago.
Hello.
How are you?
I'm well. I hope I should also get down to see you in Colombia one day. Maybe I should do a trip for you and Renato. Another time, Adli. Yes.
That would be great.
Hi.
That would be great. I have two questions for you. So maybe I will ask one, hear your answer, and then ask the second one.
Sure.
So the first one is about the connection between the first part of the talk and the second part of the talk. So how does different notions of arbitrariness relate to each other? So if you think about people who think that arbitrariness is part, or some aspects of arbitrariness are part of, have to do with freedom. So I'm thinking about Bob Kane. So these are cases in which an agent has to decide between two possible alternatives, has no reason to prefer one over the other. But these are cases in which the agent sees that there's a value in each of the alternatives. So becoming going to their bank meeting or helping the person, you can see that there's something to be gained in each of them. Now, the cases of mere picking in Libet are slightly different cases, because these are cases in which you know that you can obtain something, and you can obtain it in either of two different ways. And there's no reason to prefer one alternative over the other, because either of them is going to give you the result. You're going to please the researcher and raise your hand in the amount free of time. But now in these cases that you are presenting now in these games, it's a different notion of, it's a different aspect of randomness. Because there is one decision that will get you through, but you don't know which decision it is. Okay, it's going to be rock or it's going to be paper, it's going to be scissors that's going to make me a winner this time around. I just simply don't know which one it is. So I'm wondering how this, the notions of randomness that you talked about in the first two parts connect to this third notion of randomness, or kind of the results that you find over here connect with the reasons why you were worried about randomness in the first place. That's my first question.
So if you think about picking or arbitrary decisions or picking, I think there are perhaps you can think about 4 different types of picking, and I think you were alluding to some of them. You can imagine a situation where it's picking because it's exactly identical. I ask you, do you want to contribute to I don't know, homeless shelters in Los Angeles, or do you want to contribute to homeless shelters in Los Angeles? One is on the left, the other is on the right. You have to press one of the buttons. This is, everything is identical, and that's a type of picking. You can imagine another type of picking, which is if I ask you in advance, how much do you want to contribute to different things? And let's say that I know that in your case, you prefer, you're as passionate about homeless shelters in LA as you are about art classes for the poor, let's say. And now I put these 2 in front of you, and then they seem to have equal value for you. And now you have to select one of them. And that's I think a different type of picking. There's actually some evidence for that, because if I give you this kind of selection, it takes you a really long time to give an answer. Well, if I give you the first one, do you want homeless shelters versus homeless shelters, you respond very quickly. So you seem to treat the second one as like a very hard decision. Even you try to tease them apart, although if the values are really identical, if they are, then it's a picking situation. You could create a third type of picking situation where if I give you 2 things, I don't know, I guess in the US, it's now again pro-life versus pro-choice. So let's say that I give you this situation, and you really favor one rather than the other, but I tell you, no matter what you select, let's say it's a pro-life charity and a pro-choice charity, but no matter which button you press, we're going to give both of these the same amount of money, something like that. So now I've instrumentalized picking in a third way. A fourth one is really with randomness. And we've actually tried to instrumentalize randomness, tell people something like, it really doesn't matter, things are completely random. The thing is, people don't tend to believe you. People tend to look for patterns even when they're not there. If you tell them, look, this is a random number generator, you can even tell them that you just spent $1,000 buying a terabyte of random number generation from the internet, and it's all due to some quantum process that's, they would still look for patterns. And if you talk to them after the experiment and you ask them, at least many subjects, we played around with this a little bit with piloting and so on, people just come and say, no, I still think there was something there. So I agree with you that there are these different flavors of picking. I think it is, and for some of them, we've done a little bit of those studies. So that's why I could tell you that this reaction time for this type of picking, when it's the same value, when values are involved, it seems that people don't like to pick. They try to find, a way to tease them apart. So, and that's, I think, why they spend a longer time on those. But I think that at least empirically, we don't know yet enough about the differences between those two. Again, I would end by saying one more thing. I had this, in that sense, it's a limited view. I was just wondering, if people seem to equate, some people in the field seem to equate randomness with volition. I don't ascribe to that view, but it was just then of interest to me to say, well, if that's the case, how random can we be? But I agree with you that it doesn't cover all the bases of what we mean by random or by arbitrary. And as I myself just said, it's even somewhat different from other ones. So this is a complex field. And I think it actually merits more research. It's not a very well researched field. Like there's a paper out sometimes every year or two or something like that. So I think it would be interesting to know more. I should say one last thing. Most people look at randomness as, the most common use of randomness in neuroscience is actually as a distractor task. You give somebody like a bunch of images to remember. Now you need them not to think about those images for, I don't know, a minute. So you tell them to generate a random sequence of numbers from 0 to 9 for the next minute. And it's quite hard to do. But I think that we just don't know enough about randomness. Again, I don't know if it's a satisfying answer, but hopefully. But you said you had 2 questions.
Yes. So here's the second one. So you started the second part of your talk asking a question about how random can people be? And it seemed to me, but maybe I missed the part of the talk, that what you end up with is, answering the question, how good are people instrumentalizing randomness? Which is a different kind of question. Am I wrong to think that that's where you ended up?
Can you say more about instrumentalizing randomness?
Yeah, so if you take, if you take the games, I'm trying to use randomness. I'm trying to use randomness to produce a result, correct? But that's
Okay.
not the same thing as being random. So think just as a matter of analogy, how spontaneous are people? Well, if you ask me to try to be spontaneous on a number of rounds, I'm not going to be able to be spontaneous because you're asking me to try to be spontaneous, as it were. So it's sort of a different question, I think. So I think what you have is some results to the extent that people are not very good at, instrumentalizing randomness. But that's not yet telling us about how random people's behaviors are in general. Does that make sense?
Well, but so if they were chased by a lion and they had to be random to escape, would that be a better instrumentalization? If so, I'll try to convince the IRB. But no, I'm just, so what would be a better test of randomness in your opinion?
Well, so one of the things that this kind of interactions have as a feature is that randomness is part of what, the rational solution is supposed to be, no? So I suppose these are situations that kind of force you to deploy randomness as a way of obtaining what you're supposed to be obtaining.
No, again, so what you're saying is in the pre-game and the post-game, this was a more random in the sense that you didn't have to be random, but or is that because even in the pre-game and the post-game, I tell you to be as random as possible. So you're basically trying to be random to please me. I'm trying to see, is your criticism directed at all 3 parts or just at the game part of this experiment?
No, I think all of the parts, but I'm not sure anymore. Maybe I missed. Maybe I missed something. But when you're giving people the instructions to try to be random, they're not. That's something that they cannot. They're not very good at it. That's what we got from it. So they try to be random. They can be somewhat random, but not very good. And even when they achieve it, they cannot sustain it for a long time. Is that right?
During if they have to play, so if you and I were playing rock paper, according to our results, if you and I were playing rock paper scissors, and I had to be very random to beat you, then I would become quite random. Again, I agree with Marcel's criticism there, is that am I really becoming random, or am I just becoming really, I mean, I'm learning something that I'm learning to respond in a certain way that would make me win the game. And that just happens to be random. That's a valid commentary. And again, I agree with it, and I'm asking myself the same question, and I was asking myself the same question when we did this. So if you're saying that if I ask you to be random, you're not then really random, then I guess it would require a very different type of approach to instrumentalizing randomness. Maybe something like, oh, now, sorry, there's actually somebody outside, and I will be right back. I know it's embarrassing. Give me 1 second.
I just need to read the electric meter.
Oh, you need to open the
Yeah, you can, gotcha.
Okay. Okay, this is remote stuff for you. The guy came to read the meter, and he has to do it right now. I will be back in 20 seconds. Apologies. This is, yeah, fun times.
That's right. That's right. Yeah. So we started with the question of how random can people be, but we ended up asking the question is how random can people try to be, as it were. Yep. And I think those are two different questions. And there might be reasons why it is hard for us to harness, randomness in an instrumental way.
So sorry, I'm back. This is very funny, but it's just I think it's something like illegal not to open the gate to the electricity guy when he comes to read the meter. So yes. Anyway, I see your point. I'm just trying to think how to like, you would then maybe need to just follow people in real life and try to see if under the same circumstances, as far as you can tell, they do something different or something like that. But I have to make one more apology. I have a meeting with my dean in 1 hour, and it's 1 hour away that I have to drive. So I have to excuse myself and leave now. And this is again one of the sad things about doing this remotely rather than being with you guys there. So I will have to excuse myself. I'm sorry.
Thank you very much, Uri. We'll send you the questions we still have.
Sure. Yeah, go ahead and send them to me, and I'll respond by email. Again, I'm sorry that I have to duck out.
Yeah, we all miss you here. Thank you.
Okay, bye for now.
Congratulations to your son.
Thanks. Bye-bye.